All right, let's dive right into this explainer. Today, we're unpacking a really fascinating chapter on something we deal with literally every single day, chance. We live in this world full of profound uncertainty, right? From the second you wake up, you're constantly trying to guess what's going to happen next. Should I grab an umbrella? Is traffic going to be a total nightmare? Well, what if I told you we can actually take those everyday chaotic uncertainties and translate them into strict, measurable, mathematical concepts? It sounds wild, but just like you'd measure the length of a table or the volume of a glass of water, we can actually measure the likelihood of future events. Welcome to the mathematics of maybe.
To get a solid grip on all this, here is our roadmap. We'll start with what is probability, then look at the probability scale, explore 2 ways to measure, tackle the famous gambler's fallacy, and wrap up with sample spaces and events. Let's get to it. First up, Section 1, what exactly is probability? Is it going to rain today? We ask ourselves this constantly, don't we? Or maybe it's, will our school win the big game tomorrow? Or am I actually going to win that lucky draw? Answering these kinds of questions usually involves, a whole lot of subjective guessing based on whatever's right in front of us. We obviously know the possible outcomes. It rains or it doesn't. The team wins or they lose. But without a magic crystal ball, we're kind of just guessing in the dark. We can't predict the outcome with 100% certainty, so we just have to navigate life through this foggy lens of probability.
Think about 2 kids standing outside, just staring up at the sky. This is actually a brilliant illustration of subjective probability in action. One kid might feel that intense, stifling afternoon heat and think, oh yeah, a violent thunderstorm is definitely rolling in later. But the kid standing right next to them might look up, see the blinding sun, and think, there is 0 chance a single drop of rain falls today. Now, both kids are looking at real-world evidence and interpreting it to make a prediction, but it's entirely subjective. It's all based on their own personal feelings, past experiences, and how they interpret the moment. There's no rigorous math happening here yet at all, just pure human intuition.
So, to get truly objective and scientific, we have to transition from that subjective guessing to actual math, and we do that by defining randomness. Now, randomness doesn't just mean total, chaotic, anything-can-happen energy. In the formal study of this chapter, randomness refers to a very specific situation. It's when you know the exact boundaries of what could happen, but you just can't predict the exact result of the next specific event. Think about flipping a coin. You know the universe of possibilities, right? It's going to be heads or tails. You know the boundaries perfectly. But that next single isolated flip? Totally unpredictable. That structured unpredictability is the absolute core of randomness.
Moving right along to Section 2, the probability scale.
This is where things get really cool. We map the probability scale directly from 0 to 1. This is our mathematical anchor, really the whole foundation of how we communicate chance. If an event has a probability of exactly 0, it means it is literally impossible. Like trying to roll a 7 on a standard 6-sided die. It's just not happening in this universe. On the flip side, a probability of 1 means absolute certainty. Think, blindly grabbing a red sweet out of a bag that only has red sweets. You're going to get a red one, for sure. And smack in the middle, at 0.5, we have our even chance, the classic coin flip. Everything else slides somewhere strictly between 0 and 1, from less likely to more likely. Pinning these abstract ideas to strict numbers completely removes the guesswork. It gives us a universal language to talk about the unknown.
Okay, Section 3, 2 ways to measure.
So there are 2 totally objective ways we can measure this stuff. First, there's experimental probability. This is where we actually get our hands dirty in the real world. We physically run trials, like say tossing a paper cup 100 times to see how it lands, or we dive into massive sets of past data to calculate how often something happens. Basically, we rely on actual history. Then, on the other hand, we have theoretical probability. And this is pure logic. No physical action required at all. It assumes a perfectly fair scenario where all outcomes are equally likely. If I'm holding a perfectly weighted die, I don't need to roll it 1,000 times to know the chance of hitting a 4 is exactly 1 out of 6. The math tells us the answer before the die even leaves our hands.
Let's look at how incredibly powerful this experimental or statistical probability can be in real life. Imagine you survey 50 kids in your class about their absolute favorite fruit. You find 20 prefer mangoes, 15 want apples, 10 go for bananas, and 5 like grapes. Because 20 out of the 50 chose mango, your experimental probability for mango preference is 0.4, or 40%. Okay, so why does this actually matter? Well, imagine you're the one tasked with buying fruit for an entire school of 1,500 kids. You can use your small sample data to confidently estimate that you'll need to buy around 600 mangoes, which is exactly 40% of 1,500.
This exact mathematical process, it's how global businesses forecast sales, how medical researchers understand vast populations, and honestly, how entire economies function. It's a real game changer.
Let's turn to Section 4, the gambler's fallacy.
Okay, imagine you're flipping a totally fair coin, and it lands on heads 6 times in a row. What's the chance it lands on tails on that 7th flip? Now, our human brains are absolutely hardwired to look for patterns, right? So our intuition screams that it must be tails next, like tails is somehow due to happen to balance out the universe. But the real answer is still exactly 50%. No way around it. The coin has absolutely zero memory of the past. It doesn't know or care what happened on the last 6 flips. Every single toss is a fresh start. This mental trap is called the gambler's fallacy, and it is so powerful that, back in 1913 at a Monte Carlo casino, gamblers literally lost millions of dollars betting against a roulette wheel that had hit black 26 times in a row. They were utterly convinced red was statistically due. Spoiler alert, it wasn't.
And we see this fallacy pop up everywhere, especially in games we've all played since childhood. Take a look at this ancient Jane board game. It's the rich historical predecessor to the modern game of snakes and ladders. Originally, it was this profound educational tool to teach moral lessons. Ladders were virtues lifting you up, snakes were vices dragging you down. But the actual physical mechanics of moving across the board, that relies purely on the roll of a die. If you roll 3 6s in a row, you might sit there thinking, there is absolutely no way I'm rolling another 6. But remember the casino and the coin. The die has no memory. Every single roll is completely independent. The gambler's fallacy constantly tricks us into seeing these interconnected patterns when really it's just memoryless, independent chance at work.
Finally, Section 5, sample spaces and events.
So, let's learn some of the formal language from the chapter. A sample space, usually represented by a capital letter S, is really just the master list of all possible outcomes for any given experiment, and building it means following a few strict but simple rules. First, it has to include absolutely everything that could possibly happen. Second, no duplicates allowed. And crucially, it has to be detailed enough for the specific problem you're looking at. For instance, if you just want to know if you need an umbrella today, your sample space is practically just rain or no rain. Simple. But if you're an agricultural farmer whose whole livelihood depends on the weather, your sample space needs to be incredibly detailed, like no rain, light drizzle, steady rain, heavy thunderstorms. You see how the sample space completely adapts to the depth of your question?
To give you a visual, for a single coin toss, the sample space elements are simply heads and tails. There's literally no other physical possibility. For a standard die, the sample space is the numbers 1, 2, 3, 4, 5, and 6. It represents the total, undeniable universe of possibilities for that specific random action. And here's the secret. Once you define this universe perfectly, actually calculating the probability of anything happening just becomes a straightforward exercise in simple division.
And finally, within that beautifully defined universe of possibilities, we have what mathematicians call an event. An event is really just the act of selecting specific outcomes from your master list. It's a smaller, focused subset of the overall sample space. So if your sample space is the numbers 1 through 6 on a die, an event could be something highly specific, like rolling a number strictly greater than 4. That event only contains the outcomes 5 and 6. By clearly defining both your total sample space and the specific event you're looking for, you create the exact mathematical fraction you need to measure chance with total precision.
I really hope unpacking this chapter today helps you see the hidden, elegant math underlying all the randomness in our daily lives. From predicting the afternoon weather, to forecasting business trends, or even just knowing when your own brain is playing tricks on you during a board game, probability is absolutely everywhere. Once you know the rules, you realize you aren't just a victim of chaos. It definitely leaves you wondering, where else can you spot these patterns of chance in your own life? Next time you flip a coin, make a guess, or take a risk, just remember, you're not guessing in the dark anymore. You are powerfully engaging with the mathematics of maybe.